Hi guys, I want to do the homeworks for the non-homogeneous case now. Okay, so we are in, and so I gave you two special problems. Number 25, we had a recurrence relation an is 2an minus 1 plus n plus 5. Now they helped us out, but let's ignore them, and we're going to do it our own way. So I'm just going to solve this equation, this recurrence relation, and they also say in 25c have an initial condition a0 is 4. Okay, so let's work out all the steps instead of following their discussion. We just do it our way. We start with the characteristic equation of the homogeneous. So of course this is the homogeneous, so let's write down what the homogeneous is before we make a mistake. This is the homogeneous. So the characteristic equation would be that the degree is 1, and so we have r equals 2, right? That's the characteristic equation, and this tells me that there's only one root with multiplicity 1. Okay, so that's 1.2. So we know how the general solution looks like. It is, so an, the homogeneous one. So remember, we have to now make distinction between the homogeneous solutions and the one that we really want, the non-homogeneous one. So that is equal to, well, we have this root, so 2 to the power n, times a polynomial of degree 0. Sorry, where am I saying that? Yes, the multiplicity of this root, right? Minus 1, that's the degree of this polynomial here. That is, in this case, just a constant, alpha, 2 to the n. And that's it. Step 2. Now, so we analyze Fn, the non-homogeneous part, that is n plus 5. So what we see here, we have to do three things. We have to figure out what is S, what is D, and what is M. S here is, well, it doesn't look like there is a power, an exponential part here, but that is of course because S is 1. So I remind you, the reason is that it is really 1 to the power n. Okay. Now, what's the multiplicity of 1 in the characteristic equation? Well, there's only one root, and it's not that one, so the multiplicity is 0. Let me go back into black. And then what is D? D is the degree of this polynomial, and that is 1 here. We need this information because then, so 2.2, we can write down what a particular solution, don't forget that you have to put a p here. Be very careful denoting the things as the way that I do, right? Otherwise you're going to get confused what is what. Don't call them all an, and an. Okay, so a and p, that is, well, what does it look like? Well, first of all, we have this this s that we have to power n, but of course that's just not there, so I'm not going to write it anymore. Since this is 0, this would normally be s to the power m, right, that we would get here. Sorry, n to the power m, sorry, I misspoke, n to the power m, but it's 0, so we don't have that either. The only thing that we really have is a polynomial, and this has to be a general polynomial of degree 1. So that would be a plus bn. And that's basically what they told us in the beginning. Well, they put the a's and b's in the other way, but that doesn't matter. But we got there ourselves. That's how you're going to get it on a quiz, right? I'm just going to give you a recurrence relation and an initial condition, and you have to solve it. Okay. So what we need to do, we need to determine here. These guys we determine. So you have to really pay attention. We have this unknown alpha here, and we have unknowns a and b here. These we do first, the a and b's, because this is a particular solution, and at the moment we don't have anything yet. We need to have concrete a and b. This one is the general homogeneous solution, and so we leave all the constant, and only at the end we use this fact to determine these constants. Okay, so let's plug this in. What do you have to do? Well, we have to plug in this quantity as the proposed an inside our original. Again, very important. So I'll highlight our equation in the original one, not in the homogeneous one, in the original one. So if we do this, we get a plus bn, that is an, equals 2 times the same quantity, but instead of n, we have n minus 1. So we get this thing, plus n plus 5. That one is just tagged on. That is just our fn that we just write on the back. Okay, so we have to expand this guy here, and let's look for, let's expand it first. 2a plus 2bn minus 2b plus n plus 5, right? Take your time in working this out. On a quiz, you have more than enough time, so take your time, very easy, one thing at a time, because if you start combining steps, that's where things go wrong. Okay, so now I'm trying to combine the things, the constants, the ones that have no n in there, that is these guys, and then the ones that have an n in there, I factor the n out, I find 2b plus 1. Yeah, okay, yes. So then, now comes the point is that we have two polynomials. So let me highlight them also. We have this polynomial on the left hand side, and we have another polynomial, I'll use a different color, let's call it blue, this polynomial. And the question, the point is that they're equal, and this can only happen if the constants are the same. So these two guys are the same, so these have to be the same, and these two guys have to be the same. So this means that a has to be equal to 2a minus 2b plus 5, and that b has to be equal to 2b plus 1. It's again a linear system of equations, but this actually, often it's already solved, much easier to solve, because look at this last equation, you can solve for b here, right? If I bring the minus 2b on the side, I get minus b is 1, so b is negative 1. B is negative 1, and I can plug this in here. Now, I should perhaps also have brought the okay, let's write it. A is 2a, b is negative 1, so minus 2 minus is plus 2 plus 5. So that means that minus a is equal to 7, so a is equal to minus 7. Okay, so we have our particular solution. A solution to this recurrence relation is therefore minus 7 minus 1 n. A and b, right? This is, I'm using this formula. And now comes step 3, where we put things together. So step 3.1 is the actual solution. An is now the homogeneous general solution plus this one particular solution that we found. The homogeneous one was alpha, where was it? With alpha to the n, plus the alpha is still undetermined, luckily, because we need to, we're gonna have to make sure that we have satisfied the initial condition. We need some leeway to do that, right? But this particular one is done. That is, let's write a bit of negative sign here, minus 7 minus n. And so what do we do then? We don't plug it into an equation anymore because it satisfies it, right? If you want to plug this into your recurrence relation, what should you get? You should get that it actually all cancels away, because this for every alpha you have a solution here. But we want one specific one. We want a0 to be equal to, what was it, 4, I guess, right? Yeah, a0 is equal to 4. So what we do, we plug in n equals 0 in here. We say that 4, n is then 4. And on the other side, we get alpha minus 7 minus 0. So we see that alpha is 11. And so our final solution is, that is 11 times 2 to the n minus 7 minus n. That's the solution. All right? Now, number 35 was a little bit longer, but I'll do it nonetheless. It's good to see somehow what happens in higher degrees a little bit. So we had an is 4 times an minus 1 minus 3 times an minus 2. Yes, plus sorry, that's I'm writing. I want to do 34, right? It's 34. Sorry, that's 34. Sorry, I was copying it wrong. That's why I got a little bit confused here. Okay, so we have an is equal to 7an minus 1 minus 16 an minus 2 plus 12 an minus 3 plus n 4 to the n. Okay, so, and then we had initial conditions. Let me write them up already. A0 is minus 2, A1 is 0, and A2 was 5. Good. So step 1, we need the homogeneous one. So let's write down what the homogeneous one is, that we don't get confused. And I hope by now you know what this means. It's the ones where the a's are in part of it. So we don't have the last function there, and 4 to the n. That's going to be for step 3. Okay, so this is degree 3. This is the degree of the recurrence relation. There's something else than the d that we will deal with later. Okay, so this is the degree of the recurrence relation is 3. So we know that the characteristic equation is going to be of degree 3, and so we go down with powers of r. This is what we get. Then we have to solve this. Oh, bringing the rest on to the other side is 0. Okay, so to solve the roots, we have to look for the divisors of minus 12. That is plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6. Oh my god, quite a lot, right? Plus minus 12. Let's hope that we don't have to look too long for it. If I plug in 1, what do I get? 1 minus 7 plus 16, 17 minus 19. That doesn't work. That's pity, right? We always like this. What about if I plug in negative 1? I don't think that's going to make a difference. In fact, everything becomes a negative, so it's not going to work. So, okay, these are out. What about 2? That is 8 minus 28 plus 32 minus 12. And that seems to work, because that is 40 minus 40, that is 0. So, yes, I find that r is 2 is a root. Good. That means that I can factor this thing. Sorry, allow me to erase this. So this is r minus 2 times a quadratic. And to find a quadratic, we do long division. R cubed minus 7r squared plus 16r minus 12. We divide by r minus 2. By r minus 2, right? Make sure that you write things always correctly. Okay, so we r squared times, we can put this r in r cubed. So we get r cubed minus 2r squared. We subtract. I'll do this with changing the signs, minus and pluses here. So we get, therefore, minus 5r squared. And therefore, we get here minus 5r, right? This r goes minus 5r times in this minus 5r squared. So we get here minus 5r squared plus 10r, right? And multiply this with r minus 2. Let me undo these things before otherwise it gets too crowded. And then again we subtract, meaning that we change the signs. This becomes a plus sign, this becomes a minus sign. And we see that this cancels, of course, and we have a 6r. And then that's, so in other words, 6 we get here. And that's what gives me 6r minus 12. And we have to subtract, and of course they cancel out. Now the 6r, sorry, the line is, I don't know where that line came from. Let me subtract again quickly before you get completely confused here. Okay. And now I add that 0, but these two add up also to 0, which we need. Okay, so we know that this factor is r squared minus 5r plus 6. So we can factor that further. So we know that our characteristic equation can be factored as r minus 2. Sorry, let me write this. Good. R minus 2, and then these two numbers that multiply to 6, r minus 2 and r minus 3, right, and add up to negative 5. Don't leave it that way, because we need to figure out the multiplicities. And so we have here something multiplicity 2. So this r minus 2 squared r minus 3. Okay, so r is 2 has multiplicity 2. R is 3 has multiplicity 1. You remember, this is very important, and for one thing, it's important in writing down what the general homogeneous one is. The general homogeneous, we go for every root. So this root has 2 to the power, that's 2 to the n that we get. And in front of this, we get a general polynomial of degree 1 less than the multiplicity. So that is alpha plus beta n. Plus, we also have this root, so we get a 3 to the n. And here we get a general polynomial of degree 1 minus 1 is a 0, in other words a constant. But be careful, we have used alpha and beta, use a different constant. Okay, and that's it. We don't do anything anymore, because now we go to step 2, where we look at f of n. So f of n here is n4 to the n. n4 to the n. So we have to determine what is s, what is d, and what is m in this guy. S is 4 here, right? This is the exponential part, if you want, the geometric part, that is the base of that is my s, and then the multiplicity of 4, let's already fill it in. Well, we know what the multiplicities are, and we see that this multiplicity is 0. Now, what is d? Well, that's the degree of this polynomial, which is 1. Therefore, this means that a particular solution will be of the form, this guy, 4 to the power n, times a general polynomial of degree 1. Now, be careful. It's just because there was no constant term, that means that we do not need to write a constant term. We do need a constant term, so we have to write a plus bn here. It's a general polynomial of this degree. Okay? If you would just take the linear term, that is not general enough. Okay. And then in front of that would be n to the power 0, but we don't have that. Okay. So, now what? We have to find a and b, and we do that by plugging into the recurrence relation. So, let me see whether I can copy this thing, because otherwise it's going to take forever for me to copy all this thing, and I'm probably going to make mistakes. Oh, that's not the one. I need this one. Sorry, it's this one, right? Because it's the original one I told you, right? So, okay. So, how do I do this? Copy, I guess. I don't know. Did I cut it now? It's been a while that I've done this, so I'm not sure that I'm doing it right. Let me see what I paste here. Oh, no, I didn't copy. Sorry. I'll try it one more time and then I copy it. What did I do wrong? No. Yeah. This. And then what? Did I do copy here? Oh, okay. So, okay. Let me just move it. That's even easier. I don't need to copy it. I can just move it. Come on. Here we go. Here we go. Here we go. Okay. So this has to be plugged in here. Okay, we do that. A plus bn 4 to the n. That is an. Now the same thing I have to write here, but with an n minus 1. All the n's are replaced by n minus 1. This is what happens. Okay, then minus 16, again, a plus b, but this n becomes now n minus 2, and also this power is n minus 2, plus 12, a plus b, n minus 3, 4 to the n minus 3, I hope you see where all these numbers come from, plus n 4 to the n. Okay, the first thing we do is divide away as many powers of 4 as we can. That would be the lowest power that we have is this power, right? So we're going to divide by, so divide everything by 4 to the power n minus 3. Let's see what we get. So we have a 4 to the power 3 here, that is 64. So 64 a plus bn equals, here we're going to have 2 powers of 4 left. I hope you see that. Remember, dividing means subtracting exponent, right? So n minus 1 minus n minus 3. That would be 2, right? Okay. So we have 16 times 7. Oh, that's a bit of a 71. 16 times 7. That is 42. And 16, that is 202. No, what am I saying? Yes, 202. A plus bn minus b. Then we have a 4 here, so minus 64, there's a minus sign, don't forget that. A plus bn minus 2b. I'm expanding this, right? And then this, there's nothing here, so we have just plus 12 a plus bn minus 3b. And then this one, what we have here, plus n. And for the third power we are left with for third power is 64. Okay, so that's what we have now. So I'm gonna expand everything. Well, what we know is, and sometimes because it's a lot of writing if you do, let's look at the constants in both sides. We know that they have to be the same, and then here we go to the linear term. Right? Because this polynomial on the left-hand side is the same as this polynomial on the right-hand side. So whatever constant, the constant part of this polynomial must be the constant part of that polynomial. It's a little bit less writing. The constant part here is 64a. What's the constant part there? We have 202a minus 202b minus 64a plus 128b plus 12a minus 36b, and that's it. Okay, so and then the linear term, we have 64b, that's this part, right? And then here the terms with the n are these guys. So we have plus, is equal to 202b minus 64b plus 12b plus 64, right? So here there's no b here, be careful. Okay. So we see that we can actually solve here with the last one we can solve for b, right? So let's see what we get here. Bring everything to the other side, so we have 128b here, and then we have a minus 202b. So I bring this to the other side, that becomes 102 minus 2, and then plus 12, that becomes minus 12b. So all this together is, okay, I'm going to make mistakes, guys, because I'm really bad in doing this in my head. So 72 minus 84b, and that is equal to 64. So I find that b is equal to 64 minus 64 over 84. I apologize that these numbers are not very nice, but as I said, it's almost impossible not to have fractions. This is a little bit of an ugly fraction, but yeah, what can we do? I hope I didn't make a mistake. If I make mistakes, please, these mistakes are just numbers, right? There's nothing essential going on here anymore. This is just finding the numbers. And then from that, we have to find a, which is even more of a nuisance. Let's solve here for a. Let's bring everything in terms with a to this side. We have a 64 minus a 202 plus a 64. And then we have what else? Minus 12 a equals, and then what on the other side we have the stuff with b, right? We have a minus 202 plus 128 minus 36 b, and we know that b is minus 64 over 84. And so this tells me what a is. This number I kind of already calculated. This seems to be the same as minus 84. A equals this number. What is this number? This is 72, and 36 is 108 minus 108 times minus 64 over 84. So if I solve for a becomes minus 108, no, plus 108, minus becomes 108 times 64 over 84 times 84. Okay, this is really ugly, so I think I probably made somewhere a little calculation error, because I wouldn't expect it to be so bad. But with this textbook you never know, they sometimes do. So if I made a mistake, please try to find the mistake that I made if it doesn't come out nice. But we do find a and b. That's the whole point. We can find a and b, and so we know what a particular solution is. So a particular solution is where did I write it up here? This one here. Okay, so we know. And so now step 3, the general homogeneous solution. Well, we have to have this guy here. That's the general. So alpha plus beta n 2 to the n plus gamma 3 to the power n. And then we have our special solution here, plus 108 times 64 over 84 square. And the b was what? Minus 64 over 84 n. And where is, wait, I'm writing down, and there was a 4 to the power n also, and 4 to the power n. Okay. And I told you this is a little bit long and too much number crunching, that it really, it's not so interesting anymore. But let's see what would be the next step. We would put in n equals 0 to get the initial condition. Sorry, I wrote down a n n h. That's not right. This is the actual an, right? It's the sum. I wanted to write down that an is the homogeneous plus the particular. right? And so this is what we have here. So A0 would be then alpha, the beta is gone, 2 to the power n is gone, plus gamma, and here we would have that number plus 108 times 64 divided by 84 square. I'm sure you can simplify this number. Let me see. How is it? It's probably not going to be a nice number. So 108 times 64 divided by 84. All right, it's already, and then we'll divide by another 84. It's 0.97. Makes me think that it might have been had to be 1. I might have made a mistake, as I said. Let me see here. I'm going to quickly track my calculations through here, see whether I made any mistakes. 4 cubed, that was 64. That's the 64 here. Then we had 16 times 7. I did that correct, right? It is 42. No, I didn't do that correct. That's why I'm wrong. Jesus. 16 times 7. How do I... It's 42 plus 16. Where does it come from? 16 times 7. That is 42 plus 7. That is 112. Okay. So I wrote 202 and that had to be 112. So let's see what the difference is, what it makes. This becomes 112. That's the only thing that changes. So this becomes 112. This becomes 112. Everything else stays the same. So this is now also 112. Okay. So therefore this would be yes, we were doing this here. So this would be 112. So we have 128 minus 112. That would be 16. Yeah, minus 12. So, oh, 4b. Look how nice, guys. If you see one mistake, and I'm saying that because I will give you things that, I'm not saying that there will be no fractions, but not fractions where you start screaming and running away, mommy, help me and let me go back home, come back home. So this is not what we want. So, but now we have even a nice number. B is 16. So I can plug this in here. So remember this was 112. This was 112, and this was just 16. So what we would get here, this would have been therefore just 4 again, right? Yep, and then this would have been, let's see what we get here. So that would be 16 minus 36, so minus 20. So here we will get a, okay, let me, from here on, perhaps I should rewrite everything, right? Otherwise it gets completely illegible. So this is 16. So then we get here 4a equals, what did I say? That was 16 minus 36, that's minus 20 times 16. So a is equal to minus 5 times 16, which is 50, is minus 80. Great. This is much nicer, right? Okay. And then, so now I can write down, let's go back in black, back on track, right? So step 3. The general solution is the particular solution plus the homogeneous solution. Well, I should write it the other way. First, or homogeneous, then the particular. So that would be alpha plus beta n. What are the powers here? I forgot what the 2 and n, 2 and 3, right? So 2 to the n plus gamma 3 to the n plus, now we have minus 80. No, let's not write the plus that. Minus 80. No, plus, because there's still a power here. Minus 80 plus 4, b was 4, right? No, b was 16, sorry, b was 16, plus 16n, 4 to the power n, right? Yes, 4 to the power n. Great. So, and then step 3.2, now we plug in n equals 0, then we get a0. A0, that was... A0 was what? A0 was negative 2. Okay, A0 was negative 2. So we get negative 2 equals, if I plug in 0 everywhere, in this long expression here, the only thing is an alpha there, plus a gamma, minus 80 times 1. Okay, that's it. A1, that's for this. So this is n equals 0, I should write it here, n equals 1, that was 0 I think, 0, and the other one is 5. Yeah, let me already write it up, otherwise I'm going to forget it again. Okay, so now I plug in 1, I get alpha plus beta times 2 plus gamma times 3 plus minus 80 plus 16 times 4. And then A2 is 5, that is, now I plug in n equals 2, that is alpha plus 2 beta times 4 to n to the power 2, right, plus 9 gamma plus minus 80 plus 32 times 4 squared, that is 16. Now, this is still, of course, rather ugly, but let's see whether how far we can get in this one, right? So, okay, so the first one is alpha plus gamma equals, sorry, I have to bring the 80 to that side, and that would make it 78, right? Okay. The other one is 2 alpha plus 2 beta, 2 beta plus 3 gamma equals, and then this has to go to the other side, that is minus 64, right? 70, yeah, minus 64 times 4. This minus 6, this is minus 64 times 4, that is 256. So that's 256, because it's minus 256, and then bring it to the other side, and there was 0 there, okay? And then here we have 4 alpha plus 8 beta plus 9 gamma equals, then this thing is 48, minus 48 times 16. Okay, I'm not gonna risk making this mistake. 48 times 16, that's minus 768. We bring that to the other side, so this whole thing is minus 768. So we do here, we bring this to the other side, here it becomes plus 768, so plus 768 here, this go cancel, so this is 773. Now, I want to show you that you still can solve this thing, and we have already explained that the method to do is using elimination, right? So what we do, we work with this first equation, and we're going to multiply it with the appropriate amount and add it to the others. So the first time I'm going to do, so let's do this in 2 different colors, I'm going to do times minus 2, and then add it, so everything, the whole thing by minus 2, and then add it to the next equation that cancels the alphas. So we see that we get minus 2 alpha plus 2 alpha, that is 0, we get 2 beta, and then we have minus 2 gamma plus 3 gamma is plus gamma, equals, we have to also multiply this by minus 2, that is 156, right? Okay, I'm not trusting myself in it anymore, because it's late, 156. So that is 100. Okay, and now, in a different color, I do a different color, you see what I mean? I'm now multiplying this with negative 4, both sides, and add it to this one, because then the minus 4 alpha but the 4 alpha cancel. I have 8 beta, minus 4 gamma plus 9 gamma is plus 5 gamma equals, and then 78 times 4, that is 312. And then that's, what do? We multiplying with negative, so that's negative 312 that we have to subtract, so negative 312 from here, that is 461. And this is the system that we left with. We can solve for gamma, or we can also do again with a elimination, but let's solve for gamma. Gamma is 100 minus 2 beta, and we plug that in here. We get 8 beta plus 5 times 100 minus 2 beta is 461. So we get 8 beta plus 500 minus 10 beta is 461. And for some reason, again, this is not a nice number. At least they could have made these nice, but okay, it isn't. But the reason might be because I made a mistake somewhere again. Okay, I'm not really gonna check whether I made a mistake, because they are not really crucial, these things. I hope you understand there's a difference between this number crunching, where you lose perhaps half a point if you do this wrong, or getting just the wrong degrees, or the wrong powers, or the wrong propose the wrong kind of solution, right? That's what the essential is. So okay, this is minus 2 beta equals, bring the 500 to the other side, that becomes minus 39. So beta apparently seems to be 39 over 2. That from that I can get gamma. So gamma is then 100 minus beta, yes, yeah, beta, so 100 minus twice beta, so minus 39, that's actually a nice number, so that is 61, that's gamma, and this is beta, and then alpha, 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 from here we see that alpha plus the gamma was 61 is 78, so alpha is 78 minus 61, that is 17. So, all long story, what is the solution? Alpha 17 plus beta plus 39 halves n, 2 to the power n, right? This was the power of 2, yes. Then we have the power of 3 with the gamma, that is plus 61, 3 to the power n. And then we have the non-homogeneous part that came from the non-homogeneous part, that is minus 80 plus 16n, 4 to the n, and there's a plus here also. Okay, you see, it's quite long, right? And that is not surprising because this is degree 3. So degree 3 means 3 unknowns in homogeneous. Also, this guy here, where am I? No, I'm going too far. Well, because I erased it, so I don't see it. Where is the actual one? Where did I go? Oh, no. What did I do with the actual one? Ah, here it is still. Okay. This is degree 3 and this is degree 1, which also makes the go up. Both make it more complicated. Okay, they are different degrees and you should not confuse them, but they make things more complicated. Okay, I'm going to leave it with these two problems. I'm going to also give you some review because, of course, a quiz. That's what's coming next.